Prior to humans, the levels of atmospheric carbon dioxide were regulated by plant life, animals, and other environmental factors. However, with the arrival of human carbon producers such as trains, power plants, and cars, CO2 production has drastically increased to concerning levels. Thus, we are motivated to mitigate CO2 levels using several means including capture. With this method, CO2 can be captured directly from the air. However, this method is not practical due to the low concentration of CO2 in the atmosphere. Fortunately, the collection of CO2 from sources of production such as power plants appears to be a much more feasible option. Captured CO2 can be stored in underground saline formations and depleted oil reservoirs. Additionally, captured CO2 can potentially be converted into a variety of useful chemicals and fuels, for instance, focusing on CO2 conversion to methanol. Methanol is a particularly valuable product as an alternative fuel source for combustion engines. It is also used as a common solvent and an important feedstock for producing useful chemicals such as formaldehyde. Industrially, methanol is produced on a copper zinc oxide aluminum oxide catalyst using a carbon dioxide, carbon monoxide, and hydrogen mixture. The active site on the industrial catalyst has been identified as a copper zinc decorated step surface. This zinc decorated catalyst has been shown to be more active towards methanol synthesis than copper alone. Furthermore, it has been hypothesized that zirconium decorated catalysts can result in similar effects towards methanol synthesis. Thus, we computationally investigate the incorporation of zirconium into different morphologies of copper-based catalysts to design efficient catalysts for the chemical transformation of CO2. Interestingly, we have found that CO2 can easily adsorb on the copper zirconium catalyst, which is an important step towards the conversion of CO2. Looking forward, the best candidate materials from our theoretical investigation can then be synthesized and packed into reactors. These reactors can then be installed at the sources of CO2 production to convert CO2 to valuable chemicals and fuels such as methanol, which would enable the Earth's plants to once again balance the carbon cycle.